Hello everyone, welcome to Study Zone. Today I am going to explain the topic, that is proof techniques in discrete mathematics. So there are mainly 4 proof techniques in discrete mathematics, and they are direct proof, proof by contraposition, proof by contradiction, and proof by cases. So in direct proof we can also call it as if-then statements, because if we assume, here there is if, right? P is true, then here comes then we can say Q is true. Okay, that's why we call it as direct proof. And then we have proof by contraposition. Here we have P implies Q is true. Okay, and then we are taking the negation of this one, which means if P implies Q is true, then negation Q implies negation P is true. Okay, we are taking the negation and also we are reversing these terms, and we are telling negation Q implies negation P is true. And then we have proof by contradiction. So in the proof by contradiction we have contradiction means negation, right? So here we are false statement or negative statement, right? So here we are taking negation P implies R and negation R, which implies P. Here we are taking not P, and we are getting P. So with the help of contradiction, which means today it's raining, but we are taking it's not raining, and then we have to prove that it's raining. Okay, with the help of not raining, which means with the help of false statement, we are proving that the statement is false, so it is raining, like that. Okay, and then we have proof by cases, that is P implies Q. How we are proving P implies Q? We have P implies R, but R implies Q, which means P implies Q, which means here P is related to S is related to Q, that's why P is related to Q. This is 4 proof techniques in discrete mathematics. So let's go through them one by one in brief. Okay, so the first proof technique is the direct proof, that is if then. So in direct proof what we are doing is we assume that antecedent is true. So what is antecedent? Here P is an antecedent. So for your reference I will write here. Here we have P as antecedent. Okay, so we assume that P is true, that is antecedent is true. Then we use rules of inference. So what is rules of inference? There is modus ponens, modus tollens, many more are there, right? If you didn't go through this video of these rules of inference, please go through that and come back to this video. Okay, and then axioms, definitions, or some previously proven theorems to show that consequent is true. So what is consequent? This is the consequent. So here we are using antecedent as true, or we are assuming it as true, and then we are going to prove that consequent is true. Okay, so let's take one example and then prove the direct proof method. So prove n is odd, then n square is odd. Look here we have if n is odd, then n square is odd. So if there is if then we have to go for direct proof method. So we have P implies Q, right? So what is P? N is odd. So please remember one thing, if we have to prove anything like this, if there is even numbers, then we have to prove we have to take n as 2k. Okay, remember this one. Why? Because 2 into 1, let's take k as 1. Okay, 2 into 1 is 2. What is 2 into 2? 4. What is 2 into 3? 6. So if we go on like this, if we multiply anything, if we take any value of k, then the answer will be even number only. So we are taking n equals to 2k. And then for odd number we are taking 2k plus 1. So look here we have 2. What is 2 plus 1? We have 2 plus 1 as 3. And then what is 4 plus 1? 4 plus 1 is 5. So if we take anything like 2k plus 1, it will be 100% odd number. So we are representing even number as 2k, odd number as 2k plus 1. Okay, so this is for basic. Here we have odd number, so we have to take this 2k plus 1. Okay, so assume, so in direct proof what we are taking? We are taking antecedent is true. So assume n is odd integer. Then n equals to what? N equals to, for odd we have n equals to 2k plus 1. Then k belongs to z, z means integer, and then we have n equals to 2k plus 1. So here we have n square, right? So square on both sides. So look here, here we have n square equals to 2k plus 1 whole square. We can apply a plus b whole square formula, that is a square 2k square, which will be 4k square, and then 2ab, that is 2 into 2ab, that is 2 into 2k, it will be 4k, right? 2ab will be 1, right? 2 into 2k plus 1 will be 4k only, plus 1, that is a square plus 2ab plus b square. So if you feel it confused, you can take it as 2k plus 1 multiplied by 2k plus 1. That is also correct. Okay. Now we have 4 here, 4 here. Okay. So we can take 2 common outside. Okay. So from these two we can take 2 common outside. So if we take 2 common outside, it will be 2k square, plus if we take, now we are for this one 2k plus 1. I am replacing this with r. Okay. Because we have odd numbers as 2k plus 1. We have to take these to this format only. So it will be 2r plus 1. So here this one is in the form of 2k plus 1. So where r equals to 2k square plus 2k, where r belongs to z, therefore n is odd. Sorry, n square is odd. Okay. This is the proof for if n is odd, then n square is odd. So you can try same thing for even an integer. We can prove that n square is even also. Okay. Okay, we have second example, that is prove sum of two even integer is even. So we know that about direct proof method, that is P implies Q, right? So how to reshuffle it? Like P implies Q, that is if I add two integers, sorry, if I add two even integers, then sum is even. Okay. So we have if here and we have then here. So if I add two even integers, then their sum is true. So sum is even. So how to prove that? 2 plus 2. What is the value? 4. 2 plus 4. It will be 6. If we continue, then it will be even only, right? So let's take, I have two even integer. One is a and another one is b. Okay. So I will brief you that if I have two integers a and b, let's take a equals to 2m, b equals to 2k. Okay. So if we add those values, let's see what will happen. Okay. So if I have two even integers, assume a and b are even integers. Then a equals to 2k and let's take like a equals to 2k for some k belongs to z, and b equals to 2m. Okay, a equals to 2k and b equals to 2m for k belongs to z and for m belongs to z. So what we have to do now? We have to add a and b, right? So a plus b equals to 2k plus 2m. So now here common thing is 2. Let's take 2 outside. If you have any confusion about k and m, let's do like this one. So let's take k equals to 1 and then m equals to 2. 2k means 2 into 1 plus 2 into 2. It will be 2 plus 4, right? I have to take common outside. It will be 2 into 1 plus 2. Okay, so same thing, 2 into k plus m. Now what I am doing is I am adding these two, 2 into 3, right? Here I am adding these two, or I am taking these two terms as r. Okay, or I am adding these two, it will be 2r, which means here r is 3, right? So 2r. So this is of the form of even number, right? We have to represent odd as 2k plus 1, even as 2k, right? So This is in the form of 2k. So, where r equals to k plus m and r belongs to z, therefore, sum of two even integer is even. This is how we are proving direct proof. Next we move on to the proof by contraposition. Okay. So, the first example for proof by contraposition is if n is an integer. If n is an integer and 3n plus 2 is odd, then n is odd. So, here if n is an integer and 3n plus 2 is odd, is p, right? Is p. Then n is odd is q, right? So, in contraposition what we are taking? Here we are taking the fact of p implies q, then we are taking negation q implies negation p, right? So here we have q as n is odd. So we are taking the next thing, that is negation q is true. What is negation of q? N is even, right? Don't get confused. We have p and q. We have to take q and we have to do the negation of q, and we have to assume negation of q is true, and then we have to prove negation of p is true. Then if that is true, then p implies q will be true. Got it? So what is negation of q? N is even. So we have to prove, assume n is even. So n equals to 2k, where k belongs to z. Okay, so here we have 3n plus 2, right? So 3n plus 2. What is the value of n? We have n equals to 2k. So 3 into 2k plus 3n plus 2, right? Plus 2. 3 into 2 is 6. 6k plus 2. So here I am taking 2 common outside. 2 into 3 is 6. K plus 2 into 1 is 2. So here I am replacing 3k plus 1 with 2r. So now here we have n equals to 2k, and here we have 3n plus 2 equals to 2r. Therefore this one is also even. So therefore 3n plus 2 is even, which means negation q implies negation p is true. Therefore we can prove that p implies q, that is 3n plus 2 is odd. We can prove 3n plus 2 is odd, then n is odd by the proof of contraposition. Okay, and then let's go to the second example. So here same thing, in the place of odd I am taking even there. If you can try this, please try on your own. Okay, so if you want to try, please pause the video and try it. Now I am going to solve this. Okay, so if n is an integer and 3n plus 2 is even, then n is even. Simple. Can you tell me? This is p, this is q, right? What is negation of q? Negation of q is, here we have n is even, so negation of q is n is odd. So we have to assume n is odd, right? So I am assuming n is odd. So how to represent odd numbers? Even numbers are represented with n equals to 2k. Odd numbers are represented with n equals to 2k plus 1. Clear? So n equals to 2k plus 1, where k belongs to z. Now we have same thing, that is 3n plus 2. So we are taking the same thing, that is 3n plus 2 equals to, in the place of n we have odd integer, that is 2k plus 1 plus 2, right? So 3 into 2 is 6, 6k plus 3 into 1 is 3 plus 2. Clear? Now for odd number what I need? I need plus 1 in the end, right? So I am leaving this plus 1 here. I am writing these 2 as 6 plus 6k plus 3 plus 1 plus 1. I am leaving this 1 plus 1 as it is. So it will be 6 plus 4 plus 1. So it will be 2, 6k plus 4 plus 1. Clear? And then we have 2 into 3k plus 2 plus 1. So I am replacing this 3k plus 2 with r. So now we have 2r plus 1. So r equals to 3k plus 2. So is it in the form of odd number? Yes, right? Yes, this is in the form of odd number. So therefore 3n plus 2 is odd. Same thing, write it as it is. Okay, since negation of q implies negation of p is true, we have n is even. That's it. That's the proof by contraposition. Okay, next proof technique is proof by contradiction. So here this is bit tricky. Okay, so here in this method of proof we assume a proposition is not true. So here what we are going to do, we are assuming proposition is not true, which means here there is one dog, we are assuming this is cat, and then what we have to do is we have to prove that this is not a cat. We are not going to prove this is dog. Okay, we are going to prove. So here this is, let's take this as pen. I am telling that this is pencil. Okay, so I am telling this is pencil. Now what I am going to do, I am going to prove this as this is not a pencil. How? I am going to write here and then I will try to erase. It will not get erased, right? So this is not a pencil, therefore it is a pen. Is it clear? Likewise we have to prove. So here in proof by contradiction, in this method of proof, we assume a proposition is not true, which means this is a pencil. Then through that premise and logic find a contradiction, which means this is not a pencil, which means with the help of writing and trying to erase it, with the help of some logic we are trying to prove that this is not true. Okay, or we have to find a contradiction, negation of this statement. That shows our original premise must have been incorrect, which means our original premise, that is this pen, this is pencil, might be incorrect. Yes, it is incorrect. So this is false and therefore the proposition was true. Our proposition was this is pen, right? We are taking the assumption that this is pencil, this is not pencil, therefore our assumption that is pen is correct. Is it clear? In terms of proposition, like we have to take, like for one proposition P, we are taking one proposition named P. Okay, assume negation of P is true. Just relate it with our pen and pencil example. Okay, we have one proposition P. Let's take that proposition P as P is pen. Okay, assume negation P is true, which means negation P is pencil. Then find a contradiction that shows negation P is false. How? By writing it on book and trying to erase it. By writing it on book and try to erase it. So no, this is not erasing, which means it's not a pencil. Negation P is false. So P is true. It's not erasing. That's why P is true. That is, it is pen. Is it clear? Now for an implication, assume, if we have implication, then we have to assume P and negation Q as true. In implication, how it will be? It will be like P implies Q, right? Or negation Q implies negation P, or anything. So are true. We have to take P and negation P as true. Okay, and then find contradiction, that either P implies Q or negation Q implies negation P. If it is true, then our implication is also proper. Let's try to solve some problems. Okay, let's take the first example of proof by contradiction. Okay, so in proof by contradiction, let's prove root 2 is irrational. Okay, so to prove root 2 is irrational, what we have to take? Assume negation P. This is P. Okay, here we have whole this thing is P. So here what we have to take? Negation P, that is root 2 is rational. Okay, then there exist two integers. So I think you know about rational and irrational terms, that is root 2 equals to a by b and all, right? So then there exist two integers such that root 2 equals to a by b. Okay, root 2 equals to a by b and b not equals to 0, and a and b have no common factors. Okay, so this is about proof by contradiction. And now we have root 2 equals to a by b. So now what I am doing is I am taking this square root to this side. So we have 2 equals to a square by b square. So now we are taking this to left hand side, that is 2b square equals to a square. So here we have a square is 2 times b square, right? Here we have a square 2 times b square and square of some integers, correct? Here a square is square of some integer and a square equals to 2b square. Therefore, a must be even, because if we multiply 2 with something, anything, it will get even number, right? Okay, yeah, I will explain another one example of proof by contradiction, and I will explain proof by cases in the next video. Until then, bye bye.